Hello everyone, and welcome to this first of our live video labcasts for SXPS 288. I'm Alan Kalis, I'm Module Chair, and it's great to see so many of you online. Thanks all for joining, and if you're watching the recording, then welcome as well. So in a normal year, we'd be bringing you this live video broadcast live from the Open Science Laboratories on campus in Milton Keynes. This year is a very different year, so I'm here on the webcam from home in Scotland, but I wanted to give you just a quick taste of what the labs are like, what's happening in the labs, in the hope we'll be able to go back later in the year. So here is the Open Science Labs. This is from a previous presentation. We have labs set up where we can do demonstrations live in the lab, and in another part of the building are labs that house the actual experiments that you're going to do. So here we see the Open Science Lab and an experiment that Joe and I did earlier. So some of you will know Jo Jarvis. She's one of the module authors and has worked on setting up PIRATE in the first instance, the PIRATE telescope. And we'll have a chance to catch up with Jo a little later in this session when we look at a recording of an experiment that Jo and I did previously. So for now, we're going to be working in the spirit and philosophy of the module, all working remotely, joining on the webcams with all of you joining from wherever you're joining from. So these are live interactive sessions, and there are various ways that you can take part during the session. So the first way of interacting is that down beneath this video window, we've got some interactive widgets. These are little pods that you can pop out and interact with. And we'll look at these at various stages during the session. And the first of these on the left-hand side is the interactive map. And I see some of you have been clicking away already. And so what you can do is, what I'd like you to do is to click on that map and just pop it out and just put a click on to indicate where you're joining from. And we'll take a look at that in a moment. And then there are some other widgets which we'll look at a little bit later with some votes and some questions that you can take part in as well. Down the side of the screen, you'll see a chat box, and I see there are some messages in there already, so thanks very much. And by all means, please post your questions in there. We've got some colleagues on the chat box, some of the other tutors from the module, and some members of the module team. Thank you very much for joining in as well, and they'll be able to field your questions. And then after the broadcast, we've got the post-labcast discussion forum, so any questions that you think of later or any discussions, we can continue them there on the forum. For now, what I wanted to do was to start by introducing the module and telling you a little bit more about the great experiments that we've got lined up for you, these online remote experimental investigations. And as we go through, we'll come back to the other widgets. So if you can please take a look at, as we go through the next segment, please take a look at the next widget, which is about reasons for doing an experiment. And we'll come back and look at that vote in a little bit once we've had a look at the structure of the module. So I'd like to tell you a little bit about the experiments that we're going to do. We've got some great projects lined up for you. Now, all of these have been intrinsically designed as remotely operated experiments. So although we're in these peculiar times, we're all logging in remotely, you'll be able to carry out all of these investigations in the way that they were originally designed, with you all joining in from wherever you are. And so what we're going to do is we're just going to take a quick look at the map. That's brilliant. Thank you for filling the widget in. So we can see here there's those of you who've joined from all over and indeed from further afield as well. So you're going to be working together, working remotely, collaborating remotely through the online conferencing tools and so on. You're going to be working together on these great experimental projects that we've got lined up for you. So there are three main experimental investigations, and the first of those is the astronomy project, and that's the one we're going to focus on for the majority of this session is to tell you about the astronomy project that you're starting this week. But I just wanted to quickly look ahead at the two other experiments that we've got lined up for you later in the module. So we've got a physics investigation, which is looking at properties and interactions of the electron. And in that one, you'll do two experiments. You'll do an interactive experiment where you're looking at classical behaviors of the electron, so interactions of the electron with a magnetic field. So you'll have an electron beam going through a magnetic field. You'll be able to deflect it and make measurements of classical properties of the electron, such as the mass and the charge and those kind of properties. And then in the second part, which is a live remote experiment hosted here in the Open Science laboratories in one of the other rooms, is a quantum mechanics experiment where you're looking at the interactions of X-rays interacting with electrons. And in that experiment, you'll be proving a vital result in quantum mechanics, and you're also recreating a Nobel Prize winning experiment. The third part of the module, we've got a planetary science investigation for you, and this is particularly timely at the moment. As you may be aware, Mars is making a very close pass as the Earth and Mars go about their respective orbits. Every 26 months or so, they pass close by, and we've got a particularly close pass going on at the moment. And so I would recommend, if it's clear later on or another evening this week, do make sure that you get outside if you can and take a look. You'll see Mars in the southern southeastern sky as this very bright, glowing, very distinctive orange planet. And we've got a planetary science investigation lined up for you, which is all about planetary exploration and Mars in particular. And because of this ongoing close pass, there's a flotilla of spacecraft on their way, making use of the conjunction. Flotilla of spacecraft on their way over the next few months, aiming for landings on Mars during the course of this presentation of SXPS 288, and we'll keep you updated with progress on those. And we can see here the Mars Perseverance rover, which is one of those spacecraft which is on its way for a landing. And as part of the planetary science investigation, you'll be learning about the Mars rovers that are already on the surface. You'll be working with some genuine Mars data from the Curiosity lander, and you'll be doing a live remote experiment on analysis of planetary atmospheres using technology that has been deployed on actual space missions and on actual Mars rovers, and you'll be using those techniques in that Mars atmosphere experiment. And then we'll go on and look at some Mars surface features as well. You'll end up at the end of the module doing a team project where you'll design a space mission of your own. So there's plenty to look forward to. And there are various themes as well. So as you're filling in the reasons for doing an experiment widget, which I hope you're doing now, as you're filling that in, we can think about these different themes as well. We're moving to very different distance scales here. So in the astronomy project, we're looking at a very large structure, the structure of the Milky Way galaxy. And then we're going to a very, very small scale, looking at subatomic particles, interactions of X-rays and electrons in the physics experiment. And then in the planetary science, we're investigating on an intermediate distance scale, looking at planets and comets and measuring gas mixtures. So that's one of the themes that we'll run through the module, is these different distance scales that we're investigating. Another theme that goes through the module is using different parts of the electromagnetic spectrum. So in the astronomy project, we've got radio telescopes and we've got an optical telescope. So we're using visible light and we're using radio waves to investigate that structure of the galaxy. In the physics experiment, we're using X-rays. And then in the planetary science experiment, we'll be analysing atmospheric gases. We'll be looking at molecules which interact in the infrared. And so we'll be using infrared spectroscopy there. So all of these are great investigations in their own right. We're looking at different phenomena, different distance scales and so on. And all of these are fascinating investigations and good enough reasons in their own right for doing an experiment. But let's take a moment to nip back and have a look at the next widget, which is the vote on reasons for doing an experiment. And I see we've got a number of votes coming in. So if you haven't voted yet, do just click on one of those. And that's great to see some votes coming in. So we've got some different categories here. And of course, all of these are great reasons for doing an experiment. So one reason for experimental work is simply to measure something. So we might want to measure the mass of the electron or its charge or something like that. There's curiosity to understand something like the structure of the galaxy. Investigation, yes, is as good a reason as any to find out what's going on. And I'm pleased to see that we've got quite a lot of votes. We'll say some more about this as we go through. This idea that an experiment can be used to back up some theoretical work to test a hypothesis. And that's a very good reason for having an experiment. And that leads us to think about experimental design as well. And thinking about the Mars rovers and the planets and all those spacecraft on their way to Mars at the moment, yes, exploration is as good a reason as any. So as we go through, we might come across some other reasons for doing an experiment, but certainly when we're going to think on about experimental design, which is another theme that runs through the module, testing a hypothesis is going to feature in that, and we'll have a little bit more to say about that as we go through. So thank you for selecting that one. And what we'll do is we'll come back to the widgets in a little while, and what I'd like you to do now is to look at the next one, which is about design of experiments, and think about that as we take a slightly more in-depth look at the astronomy project in particular. And I'll tell you a little bit more about what you're going to be doing. Yes, so in that widget, as you fill it in, there are 3 little entries, and you'll need to complete all 3. Put in words there that you think reflect things that you want to factor into the design of an experiment, and you'll see the results come up when you've filled in all 3, and that's the same for the next 2 of those widgets. So I wanted now to zoom in, to focus in a little bit on the astronomy project and tell you a bit more detail about what you're going to be doing there. Now, you will have already selected, been allocated to one of the 2 telescopes, to the Arrow or to the Pirate project, and whichever one of those investigations you're doing, whether you're doing Arrow or whether you're doing Pirate, you're part of an overall investigation to look at the structure and content, the makeup of the Milky Way galaxy. So let's think about the Milky Way galaxy, what it actually is. This is our home galaxy, and we can start by looking at what we can actually see when we look out from the surface of the Earth, what we can actually see of the Milky Way. And what we've got here is a view of the night sky. You need to go to a nice dark site, and we're fortunate to have the use of the observatory site in Tenerife, which is where the Pirate telescope is located. And this photograph here, this is a star field. This is the night sky as seen actually from inside the Pirate dome itself, and you can just see some bits and pieces of the telescope off to the right there. And looking up, we see the Milky Way as this milky band of light across the sky, across the star field of the sky. And we've got these clouds of glowing stars, of glowing gas, and then obscured partly by the lanes of dust going through. And we can also see some other structures in there, some clumps and clusters of stars, and that's part of what we're going to be investigating as part of these projects. But one of the tricky aspects of this is that, of course, we're inside the Milky Way. We're inside looking out. And so to get an overall picture of the overall structure of the galaxy, to find out what shape it is, the overall structure, then we need to be a bit more ingenious. We need to employ some different techniques so that we can see out from just what we can see from looking inside. Now, one thing that we could do is to look at a similar nearby galaxy. And so we've got a picture here, which is of our nearest neighbor, one of our nearest neighbors, the M31, the Andromeda galaxy. Now, this, like our own Milky Way, is a beautiful swirling spiral galaxy of stars, gas, and dust. And we've got good reason to think that this is representative, is similar, a similar type of galaxy to our own. Now, of course, we can't step back from the Milky Way galaxy. We can't step back to a distance to take a photograph of our own galaxy, but by looking at this nearby galaxy, the Andromeda galaxy, we can look at the composition, the mix of stars, the different types of stars, the amount of dust, the amount of gas, and that is similar in nature to what we see locally within our own Milky Way in the kind of picture that we saw before. And we also see in this Andromeda galaxy the clumps and clusters, the star clusters as well, similar to those that we see in our own galaxy. So there's good reason to believe that this is a very similar type of galaxy. So that's one way that we can get a handle on what our galaxy might look like as seen from a distance. And this picture, which was taken by Pirate, also gives you an idea of the kind of image quality that we're getting from the Pirate telescope. So that's looking at another galaxy and trying to form some impressions from that. Now we can start to look at the techniques that you'll be using to make investigations and measurements within our own galaxy. And so I'd like to have a look at the schematic of our own Milky Way galaxy. So this is a sort of schematic representation now of our own spiral galaxy. So on the left, we're looking down from above the disk. So we're looking at a sort of plan view. And in the center, we've got the core of the galaxy. We've got the center of the galaxy there, the galactic bulge with these sort of yellower and more orangey older stars. And then surrounding that, coming out from that, are the spiral arms. And these are picked out with bright blue, recently formed stars. These are the star-forming regions, the density waves, as the galaxy rotates round once every 250 million years. And these are the regions where new stars are being formed. So this is where we'll find the open clusters that you'll be looking at with Pirate. And it's also where we'll find the clouds of hydrogen gas that you'll be investigating using ARROW. And where the star-forming regions are, where the spiral arms are, we have these increased density of hydrogen gas, and that's emitting radio waves at a particular frequency that the ARROW telescope is tuned to detect. And so by measuring those and some ingenious calculations, we can map out the structure of those spiral arms and the shape of those spiral arms. Over on the right, we're looking at the galaxy from the side. So we're now seeing an edge-on view of the spiral arms of the disk. We're seeing those edge on, and surrounding that, we've got the core in the middle again, and then surrounding that, we've got the tenuous halo of the galaxy, which is a sort of tenuous ellipsoidal cloud of tenuous gas containing some clusters, the globular clusters of older stars. The open clusters, the newly formed stars, remain within the plane of the disk where that star formation is going on. And so with the Pirate telescope, you'll be able to observe both of those kinds of clusters, the open clusters in the disk and the globular clusters in the halo of the galaxy, the older stars. And the measurements that you'll make will allow us to categorize those and understand their sort of life cycles and origins. And then by putting the information together, whichever project you're doing, either ARROW or Pirate, there will be an opportunity towards the end of the astronomy project to publish your results, post them on the Open Studio, and you'll be able then to compare notes with the people who did the other project. So if you're doing ARROW, you'll find out what happened on Pirate, and if you're doing Pirate, you'll find out what happened on ARROW. So there'll be an opportunity to combine the results at the end. So in order to investigate this structure, you've got two very different telescopes looking at different types of radiation, but both aimed towards the same overall objective of understanding this structure of our own Milky Way. So we've got the ARROW telescope, which is a 3-meter parabolic radio dish located on campus again at Milton Keynes. And this is tuned to the specific wavelength emitted by those hydrogen clouds of gas in the spiral arms. So we're able to detect those, and with some geometry and so on, which we'll look at, able to map those out. And then we're going to go over to Tenerife, to the Pirate telescope. And this is located a big professional observatory out there in Tenerife, with lots of other telescopes and things going on. It's 2,400 meters up. So we're up above a large part of the Earth's atmosphere, and as we can see here, up above, not always, but quite often above the cloud layer and so on. So a very, very good location for observations. And whichever of those telescopes you're using, whichever project you're on, Arrow or Pirate, you'll be controlling this advanced equipment. You'll be controlling that equipment in real time, working in your teams, operating remotely. You'll be able to control that equipment and take the measurements and the observations that you need. So what I thought would be good at this point is to see both of those telescopes in action. So we've got some time-lapse sequences of Pirate and of Arrow. So we'll first start with the radio telescope Arrow, and this is a speeded up, this is a time-lapse sequence taken during an actual Arrow observing session where the telescope is being directed to different targets, different points within the galactic plane, and then scanning briefly at each point to take the spectrum. So this is exactly what you'll be doing in your own Arrow session, directing the telescope to specific coordinates and then tracking it as you take the spectra at each point to form your overall map of the galaxy. And then let's go over to Tenerife. And here we see beautiful dark sky site, which is ideal for photographing and looking at the night sky. And we've got here the Milky Way galaxy going behind the COAST telescope, which is the smaller sister telescope to Pirate. And you can see here how the telescope is again working its way through a schedule of observations, tracking from one object to the next, moving from one target, taking an image, tracking briefly as the sky moves behind it. And now we're looking north to the Pirate telescope, which is working through a night times observations. And we can see here the night sky rotating around the North Pole star through the course of the evening. And again, the Pirate telescope, as you'll be doing during your sessions, being directed to take images of different targets. We've got some clouds coming over towards the end, which we hope doesn't happen during your sessions. And we've ended up with this composite, these circumpolar star trails showing the motion of the night sky through the course of your observing sessions. So at this stage, we're in the first week of the astronomy project. You'll be starting to look at the materials, and some of you have already booked. If you haven't already booked your slot, you're going to book a single slot where you actually get control of the telescope working in your small group. So if you haven't yet booked, do go to the booking system. There's a link to it on the study calendar and also on the resources page, and make sure that you've booked your slot. And then working together with your colleagues on that particular session, you can plan your observations working together in the forums, and then we'll hope that you have good conditions for your actual observing evening. So once you've got your data from your observing session, then there are some further steps to get to your scientific result. And so what I wanted to do at this stage was to think about the flow of information, if you like, the flow of data in an experiment like this. And we start with the telescope itself, which we can think of as a detector. So we've got a phenomenon that's taking place out there in the galaxy, radio emissions from the hydrogen gas in the case of Arrow. This phenomenon that's taking place is emitting something that we can use to investigate it. 21 centimeter radio waves in this case. And so our detector is designed specifically, the size and the electronics and so on, specifically tuned to detect those particular wavelengths because they're of interest, they're the result of the phenomenon that we want to investigate. What we get out of that detector are radio spectra. So these are the raw data sets, if you like, that are coming from the detector in the form of spectra with peaks at different wavelengths representing those radio emissions. And in order to turn those into the map of the galaxy that we want, the map of the spiral arms, there are some certain steps of data processing that you'll need to undergo. So you'll be using the Doppler shift to calculate the relative velocities of the different parts, and then you'll be doing some further programming, some geometry and so on, in order to turn those readings into the science result that we want, which is the map of the spiral arms. So we've got this flow of information from the phenomenon itself that's happening out in the universe, radio waves coming down to the detector, the signal, the raw data coming out of the detector, and then the data processing steps to turn those into the science result. And that's kind of the overall design of our experiment. And if we look at PIRATE, if we look at the optical astronomy, we'll see that that flow of information is a very, very similar process. So in this case, the phenomenon that's coming is visible light from our star clusters, and that's coming into our optical telescope as a detector. Here I've chosen a picture of one of the other telescopes at the observatory, perhaps a slightly more splendid telescope, one of the big professional observatories that's also there. And the light from those clusters is coming into the telescope as a detector. In this case, the output of that, our raw data, are these images of the star clusters that you're going to get. So here we've got a nice image of a globular cluster. And again, there are certain data processing steps that you need to take that beautiful image and turn that into some science results. And in this case, you're going to be calibrating those images, and then you're going to be measuring the relative brightnesses, the relative magnitudes of the stars in those images in order to understand the makeup of those clusters. And the output of that is these color magnitude diagrams, which are a kind of map of the characterization and distribution of the stars, types of stars within that cluster. And this will help you to understand the evolution of the stars in the cluster, the nature of the cluster, the age, and you'll be able to deduce certain other things like the distance and so on. And so that constitutes your science result, if you like, where those clusters are in the galaxy, how old they are, what the constitutions are, what the life cycles of the stars are. That's the science result. So in any science investigation, it's important to consider the overall design of your experiment, what the phenomenon is that you can investigate, what characteristics of that phenomenon gives you something that you can actually detect, that you can actually measure, and how to turn that into the science result that you're interested in. So whether you're doing ARROW or PIRATE, you're following a very similar overall process as part of this attempt to understand the nature of our own galaxy. And this is an ongoing process. It's a continuing scientific investigation. And just recently, we're in Nobel Prize week at the moment. So some of you may have seen that this year's Nobel Prize for Physics has been awarded for, if you like, a continuation, a progression of the investigation that you'll be doing, looking at the overall structure and content of the galaxy. And the prize was awarded to Roger Penrose for his theoretical work, worked with Hawking and others in developing the idea of black holes. So using general relativity to understand what happens when you have these very condensed areas of matter, whether it's from a collapsing star or from some larger structure, where gravity becomes so intense that space sort of folds in on itself and light can't escape and you get a black hole. So that was the theoretical work behind it. But what's prompted the Nobel Prize is the more recent work of Genzel and Getz, who have, again, with a large team of others, working with a large team of others, have made the observations of phenomena going on at the center of our own galaxy, stars orbiting around a very dense compact object. Here we've got some X-ray emissions demonstrating that there is a compact object, a black hole, at the center of our own galaxy. So we can put that together with your observations of the structure and nature of the galaxy, and this is something that is, bang up to date, that there's investigations continuing to go on, and the skills that you develop from doing these experiments, you may even go on and, who knows where it might lead. Now, what we could do, maybe we should put winning a prize, we should add that to our list of reasons for doing an experiment. Although it could also be argued, I suppose, many of us would also argue that the pleasure of finding something out and learning something, understanding something about the universe is reward enough itself. But it's nice to see that the investigations you're doing are sort of completely up to date with what's happening, in the wider research field. So with that in mind, now that we've seen some more detail of the investigations that you're going to be doing, let's take a look at the next widget, which I hope you've been filling in, which is about design of an experiment and factors involved in what goes into a good design of an experiment. And thank you. I can see there's amazing. There's loads and loads of responses here, and I see a big one in the middle. That's good to see. Is planning, because this is what you're going to be doing over the next week or two in your groups. So you'll each work in separate groups of 3 or 4 of you working together, and maybe later in the module in larger groups, to plan your observations. And that's very important because you get a certain amount of time on the telescopes, and it's important to know in advance exactly what it is that you intend to do. And this is exactly the same as if you were booking time on one of the big telescopes in Hawaii or somewhere. And I can see there are loads of other very, very good things here. Hypothesis, testing a hypothesis, that's a very important part of doing an experiment. Good reason for doing it. It's got to be repeatable. Yes, you've got to have control of all the variables and all of these things. So that's absolutely great. So thank you very much for all of those suggestions. And what I think I would like to do at this point is to actually now look at some real experiments going on. And so as we do that, we'll see what kind of skills that you need as an experimenter. And so the final widget, which I'd ask you to look at now, and we'll come back to it in a little bit, is about the skills that an experimenter needs. And one of the things that we'll do as you go through the module, interspersed with the experimental investigations, you'll have these skills weeks. So you've had one already introducing you to the programming and so on. And this year, the full moon is coming up in a couple of weeks' time. So the next skills week, which is based around the full moon, will come up in a couple of weeks' time. Now, full moon doesn't affect ARROW observations, but we take a break at that point because obviously the full moon will make it more difficult to get observations with PIRATE, so we avoid the full moon week. So in between the investigations, you'll have the skills week where you can work on your programming. We'll look at communication skills, how to interpret scientific papers, those kind of things, and also some more about experimental design and handling experimental data. So those will break the module up as well. You'll develop those skills as you go along. So we'll come back to that final widget after we've had a look at the next segment. And normally what I'd want to do at this stage is to do an experiment live in the lab. Now, although we're unable to do that at this point, what we're going to do is to have a look at an experiment involving optical systems. And if we think about it, both PIRATE and ARROW are similar examples. They're different types of telescope, but the principles they work on are the same. They're both reflecting telescopes. So PIRATE works with a curved reflecting mirror, and ARROW works with a parabolic reflector. And both of them work in a similar way, collecting electromagnetic radiation and focusing it to do something useful, to form an image or a spectrum or something. So I wanted to look at an experiment involving optical systems, and large telescopes tend to work on a reflector principle with a curved reflector. Smaller telescopes might use something like a lens to collect light. So you may have a small telescope or something at home, and you may have a lens-based one, and a lens works in exactly the same way. The principles are very, very similar, collecting and focusing light to form an image, maybe a magnified image. And indeed, if you have something you may have at home is a simple pair of binoculars. This is another example just of a small optical instrument, but working in the same principle. And the lens in a telescope or the mirror in a telescope or a pair of binoculars serves two important functions. First of all, it collects light or radio waves. So you've got a surface area that's going to collect a larger amount of light than you can with the eye. And secondly, it's going to focus that down to do something useful with it. But for astronomical purposes, in fact, one of the most important functions of having a large aperture, a large lens, or a large mirror is simply the ability to collect light from faint objects. So thinking about the design of the Humble pair of binoculars, this is a 50mm diameter lens on these. And if we compare that with the opening in the human eye, if you go out and look at the night sky, allow your eyes to get used to the dark, the pupil in your eye is about 5mm in diameter. That's the area that you've got to admit light. Now, if you're a little bit younger, if you're lucky enough to be younger, that might open up a little bit more, maybe 6 or 7mm. For me, it's about 5mm. And if we compare that typical pupil diameter, 5mm, to the 50mm diameter of the lens in a small pair of binoculars, that's 10 times the diameter, but of course that's 100 times the area. So even the Humble pair of binoculars, if you happen to have a set handy, is ideal for looking at the night sky. You're collecting 100 times more light with these than you can just with the naked eye. And so that's the first purpose of an optical instrument, is to collect more light so that you can do more with it. Now, these binoculars represent the single biggest increase in light collecting ability as we go up the chain of larger and larger instruments. So if you think about it, that's 5mm to 50mm, that's 100 times the area, 100 times the light gathering capabilities. To go up the same step again would be another factor of 10 in diameter. That's a 500mm, a half a meter aperture, and that's larger even than Pirate. So Pirate has some other advantages. It has a sensitive camera for collecting light, and it can integrate over a long period of time with timed exposure to collect more light. But actually, the step from the eye to the binoculars is a larger step in light gathering efficiency than from these Humble binoculars to Pirate. Nevertheless, it's great that you'll have the opportunity to work with these advanced telescopes, either Arrow or Pirate. Now, thinking about experiment design and skills, and thinking about experiments that we can do with lenses, focusing an image down to form an image, or focusing the radio waves to form the light. What I want to do now is to have a look at an experiment that Joe and I did previously in the lab with forming an image with lenses, so learning a bit more about the image forming process that's going on in the telescopes, and also thinking a little bit more about experimental design and skills. So this is an opportunity to catch up with an experiment that Joe and I did previously.
We're going to use an optical setup involving what we call a thin lens, which is something that those of you who've done S217 will know about. And we're going to form an image of a galaxy here in the lab. So we're going to start with an object, an illuminated object, and in this case we're going to use a slide. We can't fit an entire galaxy into the lab, so we're going to use a slide with an image of the galaxy on it. That then passes through a lens, and the image formed onto a screen. So there's a relationship, in order to form a sharp image, there's a relationship between the positions of the object, the lens, and the screen that's going to receive the image. So the distance from the slide to the lens, that's the object distance, and we call that U. The distance from the lens to the screen is the image distance, and we call that V. And for a simple lens, which has a focal length f, there's a relationship between these three parameters. And the relationship is the thin lens equation, which, as I say, is covered in S217 if you've done that. So those of you who've taken S217 will recognize this, that the relationship is that 1 over f, 1 over the focal length, is 1 over u plus 1 over v, the thin lens equation. Now, we can use this equation in two ways in our experiment, thinking about how we design this experiment. First of all, we can think of it as a simple measurement to measure the focal length of the lens. And we can also consider it as a test of this equation, a test of the hypothesis that this equation applies in this case. So that's a schematic, and we've actually got an actual version of this experiment set up on the bench.
Okay, so this is the real version of the schematic that Alan has been drawing. You'll notice on this side we've got a scale for you to hopefully be able to read off where we're busy moving everything around. I've got an equivalent on this side. At this end we've got a torch that's going to provide our illumination. As Alan said, we can't fit a real galaxy into the lab, so we're going to have to mock it up with a torch and a galaxy slide. And of course normally this would be a very, very long way away, because what we are essentially building here is a telescope. So we have our distant galaxy, we have our lens, and we have a screen on which we will see our focused image. And of course this represents where your eye would normally be in the eyepiece of a telescope. So at this point in time, our distance between our galaxy and our lens is fixed, and we'll be varying our other distance.
Okay, great. And Joe, what is that distance between the slide and the lens?
Okay, so between the slide, our galaxy, and the lens, which is our value of u for our equation,
Yep.
we've got a distance of 20 centimetres.
Great, so I'll note that down straight away. So we've got 20 centimetres. And being good experimentalists, of course, we want to know how accurately we've measured everything. So how accurately do you think, Joe, that you've been able to measure the position of that? What's the plus or minus on there?
Well, we've got our lens involved here, and our lens has a certain amount of depth to it. So I would say we're looking at plus minus 5 millimetres or half a centimetre.
Okay, right. So whenever we're recording an experimental measurement or an experimental result, we want to state how accurately that's been produced. So in this case, our result is 20 plus or minus 0.5 centimetres. That's the value for the object distance, and that's going to remain fixed, isn't it?
Yep, absolutely. So we're now going to change our current value of v, so the distance from the lens to our focused image, and basically see what it needs to be in order to get a focused image. So if we could turn the lights out, please. I am going to slowly move our slide representing our focal plane. Hopefully you'll be able to see that our galaxy image is slowly coming into focus. I think we're nearly there. Yeah, I think we'll go with about that. So now if you were looking through a telescope of this style, you would have a nice focused image coming into your eye, looking through the eyepiece.
Yeah, or onto your imaging detector. Great. So we've focused the image by changing v, the image distance. And have you got a measurement, Joe, of the value for that? How far away is the screen now?
So we're talking about the distance from the lens to the focal plane, our value of v, and I'd say we've got about 70 centimetres.
Okay, good. So I'll note that down, 70, and you quite rightly said about. So again, what do we think the error is on that? What's the plus or minus?
Yeah, I think my error this time is still very much focused around the lens. The plane that we are projecting onto, our focal plane, is really quite flat. So we'll take into account that lens again, giving us half a centimetre again.
Okay, great. So now I've got two measured results here. We've got the object distance of 20 plus minus a half a centimetre, image distance of 70. And so I can go ahead and start the calculation. First of all, I'm going to calculate the actual value for f. So it's 1 over u plus 1 over v. So we'll start with 20, 1 over that, and then 70, 1 over that. Add those two together, and then of course that's the value for 1 over f. So I've got to invert my result, 1 over x. And that gives me a result of 15.6 centimetres for the focal length. And now what we need to do is to work out how accurately we've measured that. And what we can do is we can go through the full error analysis later on the forums. But just thinking this through, we've got 1 over u and 1 over v. So the first thing we can do is to say half a centimetre in 20 is 2.5%. So that's a percentage error. And of course, the percentage error in 1 over u is the same as the percentage error in u. So that's plus or minus 2.5% there. 0.5 in 70 is a little bit smaller than 1%. So actually, when I combine these two, square and add, I'm going to end up with an error no more than 3%. The smaller one's going to contribute very, very little to the total. And so looking at this one, 3% on 15.6 is again about plus or minus 0.5, which makes sense. It's sort of consistent with the other centimetres. So we've got a result now for the focal length, 15.6 plus or minus 0.5. Now I think it's nominally a 15 centimetre lens, so that kind of makes sense. But here we've worked out not only the value, but how accurately we've done it. So that means that we've now measured the focal length of that lens. Or have we? What we've actually done is we've measured these numbers, we've measured these values, and we've plugged them into this equation. Now that was sort of the first part of our purpose of doing the experiment, was to measure the focal length. But of course, in doing so, we've taken this equation as an assumption. We've assumed that this equation applies in this place. So let's see if we can do better than that and test, not only do the measurement, but test the hypothesis that this thin lens equation applies to our setup. And we can do this by making a prediction, which we can then test with the experimental setup. And just looking at this equation, one thing I noticed is that it says 1 over f is 1 over u plus 1 over v. And in that respect, u and v are interchangeable. It's symmetrical that way. If I had 1 over v plus 1 over u, or if I exchange the values of these two, I should get the same result. I should get the same in focus. So how does that apply to the actual optical bench? Well, if we were to exchange the values of u and v, what that would involve would be placing the lens at the corresponding position, the symmetrical position, the other side, so that it would be 20 centimetres from the image and 70 centimetres from the object. So my prediction now is that if this equation is correct, that if we exchange u and v and move the lens to that corresponding place, I predict, we've got a hypothesis we can test now, I predict that we'll again get a sharp image. So let's try that out.
Okay, let's see if Alan has got this correct. So we have our galaxy still at this end, that is fixed. We've got our focal plane still at this end, that is fixed, and this time we are just going to be moving the lens. We've got 20 centimetres here at the moment, and we need 70. And we've currently got 70 centimetres here, so we need 20. So I'm going to take this lens and move it towards the other end of our scale. And as I approach 20 centimetres from the focal plane, I appreciate it's a rather small image, but you might just about be able to see that I do have a focused image of a galaxy again, I promise.
Great, so we've confirmed the hypothesis by making a prediction and testing it. Now, as we've noticed, in doing so, something interesting has happened to the image. We've again got a sharp image, but it's much smaller. And that's to do with the fact that the magnification depends on the ratio between the object distance and the image distance. It's v divided by u is the magnification. When the lens was over here, v was large and u was small. So this is the setup you might have in a data projector or a slide projector, projects a large image on the screen. When we switch and put the lens here, we've got a small v and a large u, and so the magnification is very small. In fact, the image is smaller than the original slide, because again, it's the ratio of V to U. So in making that further test, we've achieved two things. We found that we had a sharp image, so we've confirmed that this equation actually does apply in this situation. So we've tested or confirmed our hypothesis. And we've also learned something else. We observed a new phenomenon, which was that although the image was sharp, it was a different size. And that's led us to discover something else. So all of these are factors of a good experimental design, where you would test a hypothesis, you might discover or learn something new. You need that observation to notice what's changed when you get your result.
Great. So thanks very much, Alan and Joe. That was great to see that experiment. I think we learned something about the design of an experiment and about the process of carrying it out. So we saw how there was a certain amount of teamwork and cooperation going on, which is great. And we also learned something about the process of doing an experiment, that it's not enough just to measure something based on certain assumptions, that we actually went a little bit further than that. And we made some predictions of what would happen if we made a change to the experimental setup, so that we could confirm that hypothesis, the thin lens equation in that case. And we also observed something. So this can often happen in the process of doing an experiment. You've planned what you want to measure, but it's very, very important as you go through your experiment, an observation of something that you hadn't expected to see or you hadn't realized was going to work that way can often be very, very important and lead you to sort of some more further conclusions that you're able to draw. So in that case, we saw that the image was sharp again at the other end, but the magnification was different. So we learned something additional by good observation. And so all of these things can be factors in a good experimental design, but we're also starting to understand some of the sort of skills and techniques that we'll be wanting to use in doing our own experiments. And so what I'd like to do at this point is to have a quick look at the final widget, which I thank you very much. I can see you've been filling in, and we can see here some of the skills that we're going to need as experimenters, and that you'll be having the opportunity to deploy as you go through and do these experimental investigations. So here we've got patience, communication. I'm pleased to see here, yes, determination, perseverance, attention to detail, this observation, good communication skills, good interpersonal team working skills. You're going to be developing those as you work together in different groups, collaboration and so on, observation, all of those kind of things. These are the sort of skills that you're going to develop, and you can record these as you go through the module, as you build up your confidence in doing these experiments. Now, that was great, and we very much hope that we'll be able to return live to the labs later in the module. But we've now seen a recording of an experiment that we've done previously. And what I'd like to do now to finish off is to do some experiments live, to do some live real measurements. And what I want to do is to go live to the two telescopes, to Arrow and to Pirate, and see what's going on right now over at Arrow and Pirate. So what we're going to do is we're going to start by going over to Arrow. And here I'm logged into the Arrow telescope. So this is located on campus at Milton Keynes. So here we've got the control interface. This is the interface that you'll be using as you work with Arrow, if you're on the Arrow project. And we've got the control panel here. In the top left, we've got the webcam view. Now, it's nighttime at the moment. And as you saw in the previous time-lapse sequence, you've got a webcam where you can see what's happening with the telescope. You can just see it sort of dimly in the distance. Now, over the summer, this shrubbery has grown and it's in front of our infrared illuminator. So we'll make sure that we get that clipped back before you start your Arrow observing slots. And then the infrared light will be going a bit more on the detector there. But we've got the Arrow telescope. We're now looking at it live in real time. And you've got a control interface here. So we've got an all-sky map, and we've got the plane of the galaxy shown here on the all-sky map. And you'll be able to use this to direct the telescope to different parts of the galactic plane. You'll be able to enter the coordinates from you're planning the coordinates that you've planned to observe and move the telescope, you'll issue the commands and the telescope will move in response to those. So what we're going to do now live is to take a spectrum, a radio spectrum, with the Arrow telescope. So I'm just going to start that scanning now. And we'll see here in the scan window, we'll see the scan starting to build up. So it's working its way through the frequency range. Now that scan takes a few minutes to complete. So what we're going to do is we'll leave that running and we'll come back to it shortly. But while it's running the scan, what I wanted to do was to take us a little bit further afield, and let's go over to Tenerife and see what's happening at the Pirate facility. So here we are at the Pirate telescope. And as we can see that dusk has just fallen, so we've got a control panel here. Some of this may be a bit small for you to see, but we've got some control panels over on the left here. There's a time schedule which is telling us what the telescope is doing at the moment. We've just transitioned from dusk to night time, so the dome has just opened and is starting to take images of the sky. We've got a sensors panel here. The whole dome is equipped with an array of weather sensors, so it can tell the wind speed, the humidity, whether it's raining or not, and the dome will close automatically if the rain comes down or if the conditions are not suitable. But at the moment, we've got a beautiful clear night and the telescope dome is open. We've got the observatory manager, which is telling us what's going on with the different components within the dome itself. And then we've got the control panel for the telescope, which is telling us here the celestial coordinates, where the telescope is pointing and what the dome is open and what the camera is doing at this time. And you'll be able, during your Pirate session, to control all of this, again, according to your planned schedule of observations, to direct the telescope to the objects that you wish to image. And then over in this pane, we've got the webcam views. So we've got a live webcam view of the telescope operating. We can just make it out here. We've got an internal camera, which is dark at the moment, but what I can do is I can switch on an infrared lamp. So if I just, if I take control of the telescope briefly, so I can click on take control. You will do this during your observing sessions. So you'll now be in command of the telescope. You can issue the commands to make the telescope direct it to what you want to do. And having taken control, what I can do is I can actually switch this infrared illuminator on, as we had with Arrow. I can switch on the infrared illuminator so that we can see the Pirate telescope doing its thing. So there's the telescope in the dome. And what's just happened is that by clicking on that control in the web interface, remember this is a live view, by clicking on that control, I've made something happen thousands of miles away down in Tenerife. I've made something happen with the equipment. Now you'll be issuing more interesting commands than simply switching an illuminator on and off. You'll be directing the telescope to take the images and move to the coordinates that you want. But you'll be controlling it live in that experimental session in exactly the same way by issuing commands. So we've made something happen live in Tenerife with the equipment. We've controlled the Pirate equipment here live in this session. So very important. I've got to remember to release control now in case somebody else comes along and wants to use the telescope later. But we can see that this is what we want to happen during your Pirate sessions, to have good weather so the telescope is open and collecting data. It's got an image of the night sky here, an all sky camera, which you can see whether there's clouds coming over. And then this is this is where you'll see the images that the telescope has taken. This is one of the calibration images that the telescope runs through a sequence of calibration images just at dusk before night falls. And so this is a recent image that the telescope has taken, and you'll use that as part of your calibration process. So we've been live to Pirate. We'll come back from Tenerife to Milton Keynes, and I want to quickly go back and see what's happened with that Arrow scan that we set going a few moments ago. So here we can see that the scan has completed and Arrow has scanned through all the frequencies, and we have indeed got a couple of peaks in the spectrum here. So we've got a bump here. This is from hydrogen emissions from particular cloud of gas along that line of sight, and then we've got another small spike here, and then the rest of the spectrum. So what you're going to be doing in the Arrow session is collecting these spectra from different parts of the galactic plane and analysing these peaks, which are telling you the locations and the speeds of those clouds of gas. So that's excellent. Live during this session, we've made a radio telescope measurement, a radio spectrum of those clouds of hydrogen gas. And we've also been over to Pirate and controlled the Pirate telescope and issued some commands and got it to do something. So this is what you've got to look forward to in your experimental slots. So do remember to book up your slots. And I'll just return to the main screen now. So do remember to book up your slots, and then the very next thing, this is as part of this first week, is to start planning your observing session. Remember that you're working in teams, so I see there's already threads set up on the forums where you're discussing your observations and your plans, which is great. On the forums, you'll have support from your project specialists on the Arrow and Pirate forums, so please do ask your questions there. And of course, we've got the follow-up forum for this labcast that will be open in shortly after the labcast is complete. There will be a discussion forum, so if you think of any follow-up questions, we can have some follow-up discussion there, or if you've been watching the recording, then you can ask your questions in there. So please do visit that forum. And other than that, it just remains for me to say thank you for joining. If you've joined live, if you've been watching the recording, thank you for watching. And we'll look forward to seeing you on the forums. Very best wishes, for a great experience on your experimental projects with Pirate and Arrow. I'm really looking forward to seeing your results when you publish those on the Open Studio. So very best of luck with your observing projects. And thank you for joining tonight, and we'll see you next time.